Hey everybody, welcome to our first technical pre-lecture video. We're going to talk about probability and head our way towards Bayes' theorem. Ready? Go. So you've seen this kind of thing before. We want to denote the idea that there is a probability that an event A will happen, and we're going to draw it as this pink blob. And we have this other event, B, and we're going to talk about the idea that there's a probability that B will happen, which is potentially unrelated to A. But maybe they are related. Maybe there are certain times when both A and B can happen. So we now get to our lovely Venn diagram, where we talk about the idea that the probability that A and B both happen, that's what this notation means. Well, where is that in the Venn diagram? That brilliant bit of yellow is the place where the two circles overlap, denoting that both A and B have occurred at the same time. So there's a bunch of notations. You can write probability A and B like this, or you can use set theory, where this is known as the intersection of A and B. Speaking of set theory, we can define other things. Generically, they're not as used in the theory that we're developing, but you can write most of these ideas in multiple different ways. There are relationships between them. So the opposite of an intersection is a union, and the classical set union would be both of these circles together, including the middle part. But I could also define this union to be the exclusive OR. That particular kind of union would be written like this, that the probability of the exclusive OR, that things happen only if it's in A or B, but not in the intersection between them, I could write as the probability of A plus the probability of B minus the probability of that intersection. Okay? So again, generically, I'm just showing you the possibilities and starting to work you into the idea that mostly we can rearrange these kinds of statements of probability and put the same statements out there in multiple ways. Okay, time to work our way towards the Bayes ideas. We can talk in this case where we have two events that could overlap. We can talk about the probability of A happening given that B has occurred. You should read this little vertical line as the word given, or you could also read it as conditioned on. The probability of A conditioned on B occurring. So when we do that, we are writing a conditional probability. The statement, that probability that B has happened, we are stating that. Now, given that B has occurred, what is the probability of A? So again, we're still talking about this intersection here. But now, instead of taking the viewpoint of just looking at the intersection in relationship to everything possible in the sample space, we're only looking at that intersection given the relationship to B, the bluish turquoise circle, right? I have faded out the pink of A to make it more clear, less opaque, right? Trying to show you that A is no longer important. We're assuming the blue circle of B has occurred. And given that the blue circle of B has occurred, what's the probability that A has happened? It's that intersection. So the probability of A given B is the area of the intersection, that's the numerator, divided by the whole area of B, the entire circle. Right? That's how we write A conditioned on or given B. Okay, note the consequence of this viewpoint. We have assumed B to have occurred. Well, there's only two possibilities. Given B has occurred, either A has occurred or it hasn't. You read this symbol right here as not. So the probability that A has occurred given B plus the probability not A given B, they have to sum to 1 because these are probabilities and there's only two choices. A happened or it didn't. We're either in here or we're in here. Okay, so this idea of conditional probabilities, well, this is just algebra, people. We can rearrange this earlier statement, probability of A given B is equal to probability of A and B divided by B, probability of B. And we can just move those around, okay? So we can move this B over to here, and then we can switch sides. Okay, so we end up with the case that probability of A and B is equal to probability of A given B times the probability of B. It's just a little bit of algebra manipulation. And again, just to remind you, there's two ways to write A and B. These are equivalent statements because those are just notation. Okay, let's apply this. Let's say we've got two variables. Variable 1 is some kind of disease. Let's say it's COVID, right? So there's two possibilities. Somebody does not have COVID, or they do. All right, another variable is symptoms. As we all remember, sometimes people were sick, but they didn't have any symptoms, and that's how the disease spread well. So the symptoms are coughing, sneezing, looking sick, right? So either a person is not looking sick or they are. And this is a classic truth table, right? We're laying out all the possibilities. Somebody could be healthy and have no symptoms. Somebody could be healthy and sneezing because they got allergies. Somebody could be sick and not showing any symptoms. And somebody could be sick and displaying the classic symptoms of the disease. So the idea of a contingency table like this is to show you the probabilities of each of these possibilities. And because these are probabilities, when we sum up over every possible x and every possible y, these numbers have to add up to 1 because they're probabilities. Okay? And then we should read each box here as a particular joint probability. A joint probability is the probability of the two variables taking these particular values. So the probability that x is 0, somebody is healthy, but they are symptomatic, y equals 1. That's the probability of x equal to 0 and y equal to 1 happening at the same time, and that probability is 0.1. That's the joint probability. Okay? So, now the neat thing is, we can look at a whole row or a whole column, right? What's the probability that x is equal to 0? Well, there's two things that can happen in that case, right? X can be 0 and the person has no symptoms, or they do have symptoms. So 0.1 and 0.5. That's the probability that x equal to 0. We just add up the whole column. Likewise, we can do probability of y equals 1. Right? That's the whole row. 0.1 plus 0.3 equals 0.4. So anytime we sum up a bunch of joint probabilities to get one edge of this, either rows or columns, that is called a marginal probability. right? It's the probability that just one of the variables has occurred. It's not conditioned on anything, right? It's just the probability that one of the variables has occurred. Whereas we know from the last slide that these joint probabilities, we could rewrite them as conditional. Okay, so here's a reminder of where we're at. The probability of A and B both occurring can be seen as the probability of A given B has happened multiplied by the probability of B. This is the most general case. So it turns out that this is true if and only, sorry, we can rewrite this, I should say, right? The probability of A and B, well, this thing here, probability of A given B, it's conditional. It means that the chance of A occurring is affected by B occurring. Let me give you my A given B example, right? So what if A is I'm going out to dinner? Well, the probability that I'm going out to dinner, given that I'm currently broke, is maybe much lower than the probability that I will go out to dinner if I was flush with cash right now. Okay? So that's where the conditional matters. Did B, I am broke, happen? If it did, my likelihood of going out to dinner might be much lower than if B didn't happen. So this is the conditional probability idea here, right? So, but sometimes life is easy. Sometimes we have a situation where A is not conditioned on B, where A and B happen to be completely statistically independent. A happens with a certain frequency, and whether or not B happens, it doesn't affect the probability of A. Right? If I roll 2 dice, then the value coming up on die 1 does not affect the value coming up on die 2. So this is what it means to be statistically independent. It means that this conditional probability is the same as the marginal probability. The very definition of statistical independence is that the probability of A given B is equal to simply the probability of A. B doesn't affect anything here. And likewise, it would work the other way around. Statistical independence has to be commutative. If two variables are statistically independent, then A given B is just the probability of A, and probability of B given A is just the probability of B. Okay, let's take a little turn. I'm going to introduce a topic that's going to make our lives easier later. So this whole probability of A stuff, well, I'm going to introduce you to a magic thing where we can break up A into lots of little chunks, right? So we're just going to hypothesize that our entire sample space, the space of all things that could occur, denoted by this little omega here, right? That's our sample space. Yay for Greek letters. That is equivalent to showing you this whole box of all the possibilities that could occur. Well, what if we break up all the possibilities that could occur into a bunch of disjoint sets? Disjoint means that there's no overlap. So we carve out this region B1, and we carve out some other region B2, and some third region B3, B4, etc., up to m separate regions. M is some arbitrary number. Well, we can reconstruct A by taking the intersection of A with every single one of these disjoint unions, right? This point right here is the intersection of A and B4. And this chunk over here This is the intersection of A and B3. And here's the intersection of A and B1. So we can reconstruct A by just adding up all the intersections of A with these disjoint sets. So mathematically it looks like this. The probability of A is this intersection right here plus this intersection right here plus this intersection right here, da 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 da, all the way up to however many disjoint sets we got. Okay, now we know from the previous slide that we can rewrite any and as a conditional probability multiplied by the thing we're conditioned on, right? So the probability of A given B1 multiplied by the probability of B1. We can break this term down into the probability of A given B2 times the probability of B2. So what have we done here? Well, we can take this whole idea and we can just make it much neater by writing it as a sum from I to however many disjoint sets we made of the probability of A given the disjoint set times the probability of each individual set, sum them all up. This is known as the law of total probability. And what we did is we broke down a marginal probability, the probability of a single variable, into a bunch of conditional variabilities, right? Or really, these are actually not just conditional variabilities, but these are joint probabilities, right? We wrote a marginal as the sum of a bunch of joints. Ho ho! Right? We can break up, think back to that slide a minute ago where we did disease and symptoms. We broke up an entire column into the elements of that column. Or we can sum up all the elements on a row into a single marginal probability. Okay, so here we're at. Probability of A and B is equal to probability of A given B multiplied by the probability of B. This was the viewpoint where we started with B happening and we conditioned A given B has happened, right? We got to this intersection starting with B happening. That's how we write it here. But there's no particular reason for us to have picked B. We could just as easily have started with A, right? We could get to this intersection, the probability that B and A have both occurred, not conditioned on B, but conditioned on the existence of A happening first. So to do that, we're just writing it this way. Probability of B given A times the probability of A. That gets us to this beast here. But either way, we're talking about the same intersection, right? That's just a way of saying intersections are commutative. A and B is equal to B and A. Not hard, right? Once you don't hide it in math, it's very, very obvious. And if these two are the same thing, well, the right-hand sides of these equations are the same thing. And if you can equate the right-hand sides of these equations, well, you can rearrange them. You can just move this piece of P probability of B, divide it out, put it over on this side. Oh, magic! We have found Bayes' theorem. What Bayes' theorem enables us to do is to go from one conditional probability and place it in terms of the opposite one. Now, we just saw this, Bayes' theorem. But we can write this in a more general way using the law of total probability, right? This is a marginal. We could break it up. Remember this? We take a sample space, break it up into a bunch of disjoint sets. So if I note the idea that there are many possible B's, right? There's different B's we could be looking at. This is a particular B, B sub I. So the probability of B sub I occurring given A is equal to the probability of A given B sub I times probability of B sub I, right? We just flip this around. B given A turned into A given B. And, well, we need to normalize by the probability of A down here. But probability of A can be broken up according to that law of total probability into a sum over all the disjoint sets of all the possible B's, all the different values that B could obtain. We can just sum over all those B's and do probability of A given B times the probability of B over all the possible B values, and that is the marginal broken up into a bunch of joint probabilities. Okay, that's it. I hope you had fun. I will see you in class. Bye.